Hi, my name is Andrew McLaren, and I want to help you with mechanisms and rate laws, which can oftentimes be a bit tricky for students. And if you're in AP chemistry, they don't really explain this. They like spend a little bit of time and they're like, good luck. And most people really struggle on the actual exam. So if you have a question like this and you're trying to figure out what mechanism kind of makes sense, I do have a different video on actually writing out different rate laws when the slow step is like the second or third step. And this is basically that idea. So we're trying to look at this and think about when would be the slow step. And there's a couple different steps here. Some of them make more sense to be the rate determining than the others. So if you're looking at this reaction, it was a first order reaction. So it would make sense to me to say that this is our slow step here. Because it only has one of these things, being used to then break down, it is going to seem pretty reasonable to say that would be the slow step. You could even argue that maybe the slow step's the second one here, but the problem is that if you were to say that this was slow, this third one, that does not work. And that's because you have one of these N2O5s being used, and then one of the N2O5s needs to be used to generate just one of these NOs. So overall, if the third step here was the rate determining step, then you would have a second order reaction because two of these things are required. So you can basically think of your rate determining steps as determining how many things are needed for that rate determining step to happen. And in this case, it would only make um, sense to say that step one is slow and possibly step two. Step two is kind of a stretch, a little bit more in terms of the mechanism, and you got to be careful with that. So if we look at, I've got another problem here that kind of highlights the same sort of thing. So we've got a different reaction here. This reaction was a second order reaction that we determined from earlier parts of the problem. And then they're asking us to determine which one makes sense in terms of this being a second order reaction. And you can see that like there's two of these guys being used in the first step. And so they need to collide together, which means that they are pretty likely to be the slow step. Like that seems reasonable to me. But you have to be careful because the second step here also is only using up two of these guys to make what we need present for the second step. So mechanism two here actually does kind of work as an explanation, but it's only due to the fact that there's two of these things being required. And so if you're trying to use terms in these problems, you're going to hear something called unimolecular, which is just using one, and then there's bimolecular, and then there's tert molecular. So it just means like one molecule, two molecules, or three molecules are needed to combine. So like in a bimolecular, it's two things that need to like hit each other. And then in a tert, it's like three different things that need to be hitting each other at just the right orientation. So if you were to increase the concentration of two things that are required for a bimolecular, then it's going to end up having kind of like a squared effect on how fast the rate is. Because now you're not just having twice of one thing, but you've got twice of a second thing. So there's four times as many collisions. So it's possible that this could be like an A and a B. And so you might have a rate law where you've got the A up to like the first order and a B up to the first order. But overall, the reactions rate is bimolecular because if you double up both of these two things, it's going to end up quadrupling that rate. There's like four times as many collisions. Same sort of deal if you have tertiary. If you were to double up all three of these things, then you're going to be going up to 2 up to the third power, so times 8, the original rate. Now, these things could all be different things, but they could also be like the same thing. So you could have like two C's. So it's C up to that second power times some sort of K for that rate if you have like two different things. You can think about these unimolecular being like the first order. So this is going to be like your first order. This is going to be your second order. And then you can also have zero order. which is going to be like maybe something is catalyzed, but it only has so much catalyst available. So it doesn't really matter if you increase the amount of stuff, it's just going at the rate it's going at. Unimolecular, I do like to think of this as a radioactive thing. So it's just one thing. It's not colliding with anything, but then it's going to be separating into two new things ultimately. So it's just dependent on a singular thing. If you double up that singular thing, then you're going to be getting twice as much rate. So there's more stuff to end up breaking down in effect. So you can think of those reaction orders and how that relates here to these rate laws. You almost never see this third order, and it's kind of hard to imagine more than three things combining by hitting each other. It's very unlikely. So we don't even typically do third order in terms of like the rate laws, and we tend to focus more on these things. And I like to think of that, as I said, that zero order is going to be like some sort of catalyst or something else is limiting this reaction and how fast it's going other than the amount of stuff. So that amount of stuff is like going through some sort of bottleneck that it's like, well, this is as fast as we can go forward, and that's just what little k is. So yeah, I believe that's the big idea with mechanism is that you can think of these things as like different collisions, but you end up having to then think about those collisions and how that would then relate to the rate law, which is a little bit different than the overall reaction. So if we were to look back at this original reaction, this does kind of look like a second order in terms of its overall shape, but that is not always the case. You gotta be kind of careful with these things. So like this reaction, it looked like a second order with the overall reaction, but if you were to then look at the mechanism, it makes sense that step one would be the slow step. And therefore that would explain this first order rate law that we're observing, even though it looks like the reaction is second order. Mechanism is all about these steps, not the overall picture. All right, thank you. Bye. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there, and we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.